Right, hi, and welcome back again to part two of this video. So we built the transmitter. In part one, we tried to test this transmitter, but we ran into some issues with the software-defined radio, so we had to pause it. Now we're back to complete that tutorial. So let's do the test. So here we're gonna do the testing. So I'm just gonna list what we're gonna do. Testing, and then we're gonna look at the harmonics, right? We learned about harmonics in a previous video, so we're going to look at it in practice here. So, well, in the testing, so we're going to fire this up. So the power supply unit is right here. So we're going to be testing at 2.9 volts, and then the current is about is drawing around 0.014 amps, and the power is only 0.04 watts. All right. So that is on right now. So we're going to go to the software defined radio. And as you can see, it's already transmitting at some frequency. I'm going to turn it off. You will notice the frequency is moving around. The power is off right now. And then I'm going to turn it on. And you can see um, that movement you're seeing there is because of my hand. I'm very close to the antenna, close to the transmitter. And so you can notice that movement. So let me put it side by side. Let's see if we can put the software defined radio side by side with the, okay, right. Alright, so this is not what we wanted to do. We wanted to do the software defined radio instead. So let's make it smaller. Alright, so you can see the transmitter right there. So when my hand moves close to the transmitter, you can see the frequency moving around, sweeping as my hand is moving, right? Alright. So what we're gonna do now is to show you the harmonics. So at every frequency you see a multiple of that frequency. At a multiple of that frequency, you will see the same transmission or the same frequency. So let's make the SDR bigger because that's what we want to pay attention to right now. I'm gonna lock it in place and let's look at the SDR. Alright, so SDR here, the center frequency is around 27 megahertz. So like I said earlier on, at 27 megahertz, it's the ISM band. The this is a free band, right? Industrial, scientific, and medical frequency band (ISM). Within this range, you have free license. It's a license free frequency. So let's double this to 54, and yeah, so you can see we still have that frequency there. So when I move my hand, you still see the same impact, right? So, and that means also that around 108, we should still see the same frequency. Around 108, that's 108. So you can still see the same frequency at around 108. All right, so I'm going to turn the SDR off and back on again. Let's see. Okay, now it's turned off. I'm going to turn it back on. Sometimes it freezes. It's supposed to be a spectrum analyzer, but it's a software defined spectrum analyzer. So sometimes you get a glitch with the software. But anyways, what I'm trying to show you here is that at a multiple of the fundamental frequency, you see the same transmission over and over again. And that's why I'm going to go back to the tutorial. Let's go back to the tutorial and let's talk about what we just saw there. So what you want to do is, if you want to build this as a full transmitter for any useful purpose, you need to have a filter, a band pass filter. You want to have something like this, where your transmission is within this, and then the gap between this will be the bandwidth, if you will. This is your bandwidth, and your frequency will be in the center. So F, if this is F 0, you can call this FL, and then you can call this FH. So lower frequency, higher frequency, but you want your frequency to be centered. The center of your frequency would be here. That way, there will be no interference between you and a neighboring signal, right? So you want to use a band pass filter, and a band pass filter includes a low pass and a high pass. So you want to operate within your F layer, L and FH. Right, there might be some other terminologies for this, but you just looking at the lower end of your frequency and the upper end of your frequency. The gap between that will be your bandwidth. For FM, the center frequency, if you like, let's just call it FC for now. Between FC and FL, and between FC and FH, it's about 100 kilohertz each. So the full bandwidth for an FM transmitter then, or FM receiver, is 200 kilohertz. So that means that you can have a new channel every other 200 kilohertz. You can have a new frequency every 200 kilohertz. So when you tune your FM radios, let's try with a real FM radio here. So I'm gonna go to FM radio and let's go band FM. So normally you will have a station at every 200 kilohertz. So let's go down to, if in this region we're operating, if there are FM stations, then you get one at 106.7. The next one should be at 106.5 if they have one, or the next one will be 106.9 because you have to maintain that 200 kilohertz gap. So let's go down. All right. So that's dot one. So there should be dot three if there is one in this area, but there's none. So then the next one should be 159. Yeah. So it should be 0.7 if there is, 0.5 if there is, 0.3. Yeah. 0.3. Then 0.1 if there is, then 0.9 if there is, 0.7, 0.5, 0.3, 0.1, 0.9, 0.7, and 0.9 actually calls itself 104, but it's actually 103.9. 0.7, 0.5, 0.3, 0.1, 0.9, 0.7, 0.5, 0.3, 0.1, 0.9. So the next one should then be 0.3, 0.1, 0.9, 5, 3, 1, 9, 7, 5, 3, 1, 9, 7, 5, 3, 1, and so on and so forth. Let's go until I get to my favorite channel. Alright, I couldn't get it from this radio. Yeah, 7, 5, and so on and so forth. So you get the drill. So you need a filter to remove everything outside your range. So now if I am at FO, the 200 I'm talking about then is between me and the next guy, the next frequency here. Should this 100 kilohertz on my right is my band protection from the other guy, but that other frequency will also have another 100 kilohertz here before the center frequency, and then another 100 kilohertz here before the end of that width. So this 100 plus that 100 gives me 200. So that's why a channel is located 200 kilohertz after the next one, because there's 100 kilohertz bandwidth to the um, right of the previous one, and another 100 kilohertz to the left of the next one. And so the gap is maintained. So this is the band gap, if you will. But this is your bandwidth. Within your bandwidth, in the middle of your bandwidth, that's your center frequency. All right, so we've tested this and we've shown how this works. So I'm gonna just rehearse something I said earlier on. I probably said it too fast, so let me repeat that on this page. If you want to build an amplifier or a transmitter that you want to take the input from an auxiliary source, assume this box here to be your transmitter. Assume this to be the input. In our own case, this point of the input is where you have the 2K7 or 2K2, depending on the capacity on the resistor that you used. This point here, the rest of the circuit is here, and then your antenna, it's here. So this antenna comes from your C4. So you know what I'm talking about. Then this is R1, and this is your C1 based on our transmitter. This portion here, you can have an auxiliary input and also a microphone input. If you're using a condenser microphone, you want to bias that condenser microphone. This is positive. You can use 10 kilo ohms here. In the middle here, have a capacitor. And then here you have another auxiliary source. This is your auxiliary source. The signal comes out from your auxiliary source. You can also use a filtering capacitor or a coupling capacitor. The reason you do that is just in case this is drawn directly from a DC source, you want to isolate the power supply conditions of your inputs to the power supply conditions of your transmitter. So you can use a capacitor in this way, right? When you do that, you can use a switch here. The switch can let's just do it in one swoop. Let's use a volume control as well. So use a variable resistor as your volume control. This lower side goes to ground, the middle goes to the wiper, and then this top here goes to a switch. So this switch will toggle between. So this is your mic input, this is your aux input. Alright, so you can use to select the input. And in some cases, you want to use them at the same time. You don't really want to switch between them. You want to have, so this variable resistor, let's just use 50 kilo ohms as a volume control. Sometimes you want to have them working at the same time. All capacitors, let's just use 1 microfarad 16 volts. Let's just say, right, you can use 1 microfarad 16 volts for each of them. And if you want to use them together, so you can have the audio in and the aux in and microphone in at the same time, so you can talk as well as play your music in, you can have a mixer. You can have a mixture between the two. So what I would suggest in that case then is, instead of using this resistor as a volume control, you can just use it as a balancer to balance the input signals. So how to do that? You repeat the circuit here, or this block diagram. Let's just call it block diagram, right? Not circuit. This TX here, I'm not going to repeat all the resistors because you already understood that. So what you're going to do here is you have your variable resistor here, same variable resistor, and the wiper still goes into the middle, but this one now goes to the mic, the mic input. So I'm going to just draw a capacitor, and this is your mic input. And then this one here, I'm going to call it the aux in. All right, so this wiper then adjusts between the mic input and aux input. So as the music is playing, let's say music is playing in here from your aux, and audio. Let's say how do I say MC? Let's say just MC or the so that's will be the master of ceremony, or you, the broadcaster, you're on that mic. You can use this wiper to adjust whose voice or which volume is higher and that is transmitted from the output here, right? So as you adjust this to this point, you're speaking, hell, this is the music of the day, thanks for enjoying. As you're saying that, the music is still coming in, but very low because the wiper is further away from it. When the wiper is all the way to the mic in, the music will be cut off. But you can adjust it somewhere in the middle, and you can still speak while the music is playing in a little bit. And then when you're done speaking, you just turn it down. And the ways to one of the variable resistors to use for this is the logarithmic variable resistors. I don't have one right here to show you, but it's the one that you can slide up and down. It's a slider volume control. So it's something like this. So as you're talking, you can slide it, and your voice is coming in, and you can slide it down, and the music is coming in, depending on where you want to put it. So if you want to have your mic here, and then you have your aux here, right? So as you slide it, and if you put it at the middle, then both of them have equal. If it will be balanced, right? So balanced here. If you want to have it balanced, you can put it in the middle. So the music and the microphone are coming in balanced, equal amount, and going to your transmitter. If you want the music to play more, you slide it down. If you want your voice to come in more, you slide it up. So like right now, you can slide up and say, "Hi, ladies and gentlemen, it's 5:52 p.m. Eastern Standard Time. It's being yours truly, number one." You can say whatever you want to say. Right. All right. So let's just slide it and just close out from there. Hi, thank you for sticking around to the end. It's been an awesome time with you. Please do not forget to like, subscribe, and share this video. Until we come your way again next time, stay enthused. Then we'll slide it down and say, music out. All right.